Welcome to the third video in a series of 5 about linear regression. Correlation. Here's our first example. This particular chart shows 15 individuals, and it shows the amount of college, number of years of college they've attended, and their annual income. And the question here is there a connection between college attendance and income? Here's the same data displayed in a scatter plot to make it easier to analyze. So the first thing we want to do is a numerical analysis on our calculator. So I recommend getting out your calculator and typing in this data so we can go to the linear regression screen and do some analysis of the numbers we find. If you're not sure how to do this, I will recommend watching the video before this, Linear Regression 2 of 7, which shows how to use a calculator to enter this data as lists and so on. Go ahead and pause the video and hit play when you're done entering the data and going to the linear regression screen. Okay, these are the numbers your calculator should show. Now it won't show exactly these numbers, because I have a tendency to round everything to 3 significant figures, as you can see I've done here. If your numbers look a little different, that's fine. I've rounded and your calculator didn't. No big deal. Let's look at this last number here, which the calculator calls R. That's called the correlation coefficient. And correlation coefficients are measured on a scale from -1 to 1. More details on that later. This particular correlation coefficient is to the right of 0. 0, by the way, represents that there's no correlation whatsoever between the variables, and 1 represents a pure correlation. So our correlation coefficient of 0.48478 might land us right about there where that arrow is. Okay, let's look at another example. This chart shows data from 17 babies. It shows their age in months and their weight in pounds. Here's the same data displayed as a scatter plot to make it easier to see the relationship between the variables. Go ahead and pause the video, type the 2 lists in your calculator, go to the regression screen, and then you can compare your answers to mine. Your calculator should have given you these numbers. Again, I've rounded to 3 significant figures, and the calculator does not do that, so yours may look different than mine, but these are essentially the numbers that you should have gotten. Notice we have a correlation coefficient here, an R value that's slightly higher than the last time, 0.717, and that represents a higher degree of correlation between a baby's age and their weight compared to a person's college experience and their income. In fact, let's take a brief look back at the previous scatter plot in relation to the college and income problem to see how those dots were more scattered. This is the previous problem where we had a correlation coefficient of about 0.47. You can see an upward trend in a general upward trend in the data, but not a very tight fit line, as it were. Now watch the scatter plot as I transition from the previous problem to our current problem. Notice there's also an upward trend here, but with a correlation coefficient of about 0.71, the data form closer into a linear pattern than in the prior problem. So it turns out correlation coefficients that are closer to 0 represent a weaker correlation. Correlation coefficients that are closer to 1 represent a stronger or more statistically significant correlation. And one should ask, is there some point in between that separates weak from strong? Well, not necessarily. These are more descriptive words than they are numerical words, but also correlation coefficients aren't weak or strong merely on their own. We'll see in video 5 that the sample size plays a role in how statistically significant a correlation coefficient is. So that covers from 0 to 1 on the correlation coefficient scale. There's an analogous side on the other negative half of this scale as well that we'll talk about in a minute. But first, one more comment about the positive correlation coefficient side of the scale. In our problem where we had compared the years of college to the income of individuals, we noticed that the variables tended to rise or fall together. In other words, as the number of years of college increased, so too did income, or as the number of years of college decreased, so too did the income. We say in statistics that the variables tend to rise or fall together. As one goes up, the other goes up. As one goes down, the other goes down. The same was true in the age versus weight of the babies. As the age went up, the weight went up. And as the age went down, the weight went down. So we can also say in this case that these variables tended to rise or fall together. Both of these were examples of positive correlation coefficients. Our next example, we'll take a look at something that has a negative correlation coefficient. Let's compare a person's age to their hearing ability. Imagine that hearing ability were on a scale of 0 to 100, where 100 is perfect hearing. Okay, you can kind of tell by looking at this table that as we look at older and older individuals, their hearing ability tends to get lower and lower. Here's the same data displayed in a scatter plot that shows a slight downward trend in the data points, as you can see how they're getting lower and lower from left to right. Now, age and hearing, you can see in this example, have what we call a negative correlation, because when one rises, the other falls, or vice versa. As we look at older and older individuals, we tend to find lower and lower hearing scores. Age goes up, hearing goes down. And when there's that kind of relationship in statistic, we say when one variable rises, the other one falls. And this is the concept with which we associate negative correlation coefficients. What I'd like you to do now is pause, type this data in your calculator, and confirm that you do in fact get a negative correlation coefficient. This should be what your linear regression screen shows. And again, you can see that R is a negative number here. It's pretty close to negative 0.8, which would land us pretty close to the strong end of the 0 to negative 1 scale for negative correlation coefficients. Now, stepping away from the actual problems of college and income and baby weights and age and hearing, I've created some generic pictures of different correlation coefficients just so you can get a sense of what the data might look like. Here is pure upward trending 100% linear data. This has a correlation coefficient of 1. Notice as the correlation coefficient lowers to 0.95, we still have a very visible and noticeable upward trend in the data. Even at 0.9, it's a pretty pronounced relationship. Recall that I'm not talking about any specific variables here. There are no units or numbers. I'm just giving you a general picture of what correlation coefficients can look like. Notice as the correlation coefficient drops to 0.7, we still notice an upward trend in the data as going from left to right. In other words, as one variable increases, so does the other. Going to 0.5, it's less noticeable. At positive 0.2, there seems to be almost no distinguishable upward trend to this data, and 0 is just scattered all over the place. Literally no correlation between the data. Looking at the negative half of the scale gives us the same picture. A correlation coefficient of -1 would represent perfect downward trending linear data. As one variable increases, the other decreases, or vice versa. As one rises, the other falls. -0.95 is still a pretty strong downward trend, as is -0.9. When we get to the -0.7 region, we can still see a weaker correlation, still a noticeable correlation, a downward trend of the data, but the data are slightly more scattered. When correlation coefficient hits -0.5, you can still see a downward trend of the data, but it's way more scattered. And at -0.2, it almost looks like no correlation whatsoever. Now let's take a look back at a problem we saw earlier in this video. These are the same data that you saw earlier. These are the 15 individuals, the number of years of college they attended, and their annual incomes in a table and scatter plot form, along with the calculator results. Let's focus our attention on r squared. R squared is the correlation coefficient squared, and it's literally the number times itself in the traditional algebraic meaning of squared. But why is it displayed there? Why would the calculator bother to square it for you? You could certainly have done that yourself if you'd wanted to. Well, that's because r squared has a representation. Notice that r squared is 0.228, which is about 22.8%. Let's round that to 23 just for conversation's sake. That means that 23% of the variation in income can be associated with the amount of college attended. In other words, there are all these things that affect individual incomes. And college attendance, or the number of years of college, seems to have a 23% of the influence seems to come from the number of years of college. Well, there are other factors that determine a person's income other than the number of years of college they've attended. Whatever they are, we're not studying them in this problem. But if college attendance is 23% responsible for variations in income, then the other 67% can be attributed to other factors. By the way, 67 came from 100 minus 23. What are these other factors? We have no idea because we simply have the college attendance data and no other data to make any assumptions about. Well, that's the meaning of r squared. Here's another famous quote: correlation does not imply causation. Let me give you a sense of what that means. Just because there's a correlation between number of years of college attended and income doesn't mean that the number of years attended college is causing you to have a certain income, but it may play a role. While correlation does not imply causation, it doesn't rule it out either. It simply makes no statement about whether one variable is having an effect on the other or there's some third variable lurking around that is affecting both of these. Who knows? The bottom line is, if variables are correlated, it doesn't mean that one is causing the other. Here's a strange example. There's actually a correlation between the amount of TV someone watches and the amount of trips to the emergency room in their lifetime. And you can't deny the correlation. It's statistically there. Question: does watching TV cause you to go to the emergency room? Probably not. So that's an example of correlation between variables. There may be some third factor other than TV and ER visits that's behind the scenes playing a role in affecting both of them. And lastly, let's talk about the word tend. Based on this data, we could say that people with more college tend to make more money. Or reversely, people who make more money tend to have more college experience. Both of these would be true statements based on the weak to moderate correlation that we've found here. But I want to remind you that tendencies don't make statements about individuals. Let's compare this individual to this one. The first individual has 3 years of college and makes $84,000, whereas the second one went to more college and makes less money than that first individual. So it would be incorrect to say the more college you attend, the more money you make. People would know what you meant, but it's important to use the word tend to show that there are always going to be individual examples that don't follow the trend that you're describing. We've finished talking about correlation. In our next video, we'll look at the regression line, where we take data, find a line of best fit, and use that linear equation to make predictions about other individuals outside the data set. And that completes the third of 5 lessons.